Hello again, Internet. Picking up where I left off. Now we've got two ways of making very precise motion, circular motion. We can make a shaft spin very precisely. We can stop it in a very precise spot, and we can hold it there. And it doesn't matter if we're using a stepper motor or servo for the conversation that's about to happen. But for my examples, I'll probably just use stepper motors because it's usually easier math. So we got stepper motors. We can control rotary motion very precisely. What do we do with that? Well, one of the most common things to do with that rotary motion is to turn it into linear motion. So for that, we're going to need a couple things. First, we're going to need sort of a track, a guideway, or something of that nature that we can use that's already straight. So we could use a piece of aluminum extrusion with a V pattern in it. Then we could have a matching wheel that fits in that V. We can call that a V wheel, and that wheel can go back and forth and roll relatively smoothly assuming the extrusion is nice and clean, and assuming that the wheel is well made. We can move pretty smoothly indeed. This is very common. So the extrusion that we use for this is called V-slot extrusion, and it's basically just regular T-slot, but with a couple of 45-degree angles cut out of it, so that there's a V, so that V-shaped wheel can move in it. Now that wheel, it's got a flat, and then it's got two 45s before it goes up to the sides of it. And those two 45s are what runs on the V wheel. And the flat doesn't run, or the two 45s are what runs on the V rail. And the flat doesn't really run on anything. Okay, and so obviously just a wheel sitting on a rail, pretty easy to knock that off. So you want to put another wheel on the opposite side, and you can have a little tension or two to allow you to tighten that wheel against the rail. But even then, it's going to be kind of wobbly back and forth. So you're going to need at least three wheels. So two wheels on one side, one wheel on the other, with the one wheel on the other being the one that can be adjusted. And then sometimes you're just going to use four anyway, so two on either side, and the two on one of the sides have to be adjustable. So you put your V wheels on the rail, tighten them down, adjust them to be nice and snug. They roll back and forth. They don't rock back and forth, they just move in that one direction. They don't rotate at all, or they don't rock around or go up and down off the rail. They're nice and just one back and forth one way. So this is nice and cheap, because a lot of times you already have the aluminum extrusion, because it's like you're using it to make your frame anyway. So you just get instead of getting the T-type, you get the V-type. And it's basically the same cost as the T-type frame, but now you've got a place for your linear motion to happen too. And the wheels themselves, they're pretty cheap. It's basically just a washer, two ball bearings, and a piece of Delrin. So there's not much to that. Downsides. Mainly it's about precision. So these tend to wear. Specifically, they tend to wear in, like over the course of, say, first 100 hours. You probably want to adjust them after 100 hours, maybe after 1,000. There's kind of something that you prefer not to have in a consumer product, you know? You prefer, like, if you're selling a consumer product, you prefer it to be like very little input. And this is like kind of tricky to get the tension just right. So that's not ideal. Also, they're plastic wheels. I mean, and it's Delrin, so it does weird stuff, and it kind of can bend if you or it can deform if you leave it too long. Again, it wears in faster if you've got any kind of real loads, and it's only as accurate or only as precise as the linear rail. So as the linear extrusion. So if that's not right, well, now everything else is wrong because of that. But it is used a lot in super low end home CNC, specifically, in fact, almost exclusively 3D printers, like the cheap ones, under $200 class. So next step up from there is round rails. So you have a round piece of stainless, or ideally hardened steel, maybe stainless steel, hard to say, but it's round rod, maybe 8 millimeters or 10, 12, or even half an inch, depending on how you're designing. And you just have a linear bearing on there. And that linear bearing can either be basically just a ball bearing, so it can roll back and forth relatively quickly, relatively precisely. You can get these bearings relatively cheap, or you can spend a lot to get a really nice one, obviously, as with most things. The cheap ones do tend to be less precise, tend to make more noise, so that's a downside, and it's hard to correct that. Like some ball bearings, you can take the balls out and put different size balls in and really tune them. That's not an option with these. You get what you get. So, in theory, these are really great because they give you very precise linear movement, and they're very cheap. Downside, if you go too cheap, they're going to be garbage. And if you're not careful, you can definitely go too cheap, even while spending good money. In addition, the cheap ones make a lot of noise. And ultimately, the big problem with these is that the whole selling point is that they're cheap. And the next step up is effectively the same price. Unless you're buying in bulk and you really know your suppliers and we're talking bare minimum of a trip to a manufacturing site in another country to set this up. If you're just buying stuff on AliExpress, these kinds of bearings are kind of terrible. Alternative to these is sleeve bearings. So instead of balls, it's just a very slippery piece of plastic, or potentially oil impregnated bronze, but usually it's plastic. And these just slide back and forth. Downside with these, again, usually not super accurate, but they are cheaper and they're smaller, and they can be very useful for dirty environments. So like if I had to make something that moves back and forth in an environment where there's a bunch of coal ash or something like that, I don't want that in my ball bearings. So I'm going to use the sleeve bearing for that. Also, there are some industries where ball bearings are just very much discouraged, especially like in the food industry. Ball bearings are a big no-no. You can use them, but you have to jump through hoops. And even then you have to be like, I used these for a good reason, not just because. So in that case, sleeve bearings are just kind of the default. If you can use a sleeve bearing in such a situation, you will. So that's another advantage there. In a hospital and a graveyard. All right, so next step up. are, I don't actually have a great name for these. They're called linear rails, but the sort of the round ones. These are more rectangular, and they have holes for screws in them, so you can just screw them to a piece of extrusion, or to really to anything that you want to screw them to, for that matter. And they're kind of rectangular. They got cutouts in the sides. They're like circular cutouts to match with the size of ball bearings. Just so like one of the more common sizes is just little 2mm ball bearings. They circulate through here, through the rail, or they circulate through the bearing, contact the rail, and this gives you very precise movement, relatively quiet movement too. It doesn't wiggle around. Assuming it's tuned right, I'm assuming that they're all tuned right and made well, is that it gives you very precise, quiet, smooth movement. Downside here is they tend to be expensive. So, like the most common type that you see. Oh, maybe I should look at the hospital while I'm here. I could go to the top of that hill as long as I'm out. Might as well, right? Okay, so the most common type that you see are high wind. Or more specifically, you see clones of high wind that are dimensionally the same in theory, but they're not made as well usually. So the rails might be a little bit oversized or undersized. The bearings themselves can be a little oversized or undersized. The balls in the bearings might be very low quality. The oil wipers might be very low quality, so on and so forth. Over the years, now these have been around for a while, the clones, to the point where I don't even think they're covered by like patent laws or anything like that anymore, because it's just such an old design. But don't quote me on that. So the real ones are incredibly expensive. You're talking probably 10 times the price of a clone for the real one, and they're good quality stuff, but they're not worth the money, in my opinion, when the clones are an option. So, downside with clone, it's going to tend to be noisier and less precise. It's going to wiggle around on the rail maybe. It might make a really horrible sound, might jerk and move when you're moving it. It can be very nasty, and it's probably not going to be very good. But you can deal with that. And how you deal with that is you find the nominal ball bearing size. So for like the MGN9 series, for example, that nominal size is 2mm. What you do is you buy a few bags of balls. So you buy a bag of high quality 2mm balls. You buy a bag of high quality 1.99mm balls and high quality 2.01mm balls. And you might even go up to 2.03 and down to 1.97, so you can really cover all your bases. Then take the bearing apart, which is 4 screws, 2 on either end. Take those out. Then you can pop off these 2 little metal brackets, and the whole thing just falls apart. Take out all the old bearings, or all the old ball bearings. You'll see there's a cavity on either side that the ball bearings run down. You want to take a small thin implement, stick it down there. Make sure you don't feel an edge kind of around halfway through. That can cause your balls to get jammed up. That's not good. But as long as that's okay, basically just clean up the bearing. This is probably shipping with some really nasty oil. Put a little bit of very light lithium grease on it. Reassemble it the way you took it apart. And then you can just start putting balls in. So you might start just loading up both sides with 2mm balls. And you slide it onto the rail, which when you slide it on the rail, you want to use this little black piece that the bearing itself came with. The rail, it's like a plastic version of the rail, but a little bit smaller. It just makes loading them on a lot easier because you don't lose any ball bearings. They don't shoot out. So you load it up with 2 millimeters, you slide it onto the rail. If it wiggles around, you have to increase ball size. So you might take it apart, remove all the 2 millimeter balls from one side, and put in 2.01 millimeters. Try it again. Still doesn't work. Take out the remaining 2 millimeter balls from the other side, make all those 2.01. Then you can go to 0.2 and 0.3 if necessary, but you're probably not going to need to. That would be a very out of spec bearing. Or of course, if it doesn't go on, if you can't get it onto the rail, or you get it on the rail and it runs really rough, that means it's too tight. So you're going to have to take and maybe drop a 2 millimeter bit on one side down to 1.99. And that way, admittedly, it's frustrating and time consuming, but you're getting basically the same performance as the name brand stuff, arguably as good as like their preloaded stuff, which they charge a lot more for. And you're getting it for a reasonable price. It's just frustrating, but what are you going to do? So then, yeah, you can just, at that point, it's only slightly more expensive than the round linear rails with the ball bearings. And yeah, it's just less frustrating. Or the round linear bearings are less frustrating, but the rectangular ones just do a better job overall and end up being about the same price. So might as well go with them, in my opinion anyway. So how do you move? So we've established that you can move back and forth very smoothly. We've picked one of these bearing types and set it up, and we've got a thing attached to our bearings so the thing can move back and forth, but not in any other direction. Wonderful. Next, we need to make the motor connect to that, which the motor just spins. So in order to turn that into linear motion, we have to, we can do a couple things. First is that we can use a belt, or potentially a chain, but belts tend to be more accurate, so let's use a belt. And for like a small 3D printer, typical to use what they call GT2 belt, which is a very small, lightweight belt, and it doesn't have to be tightened super good, or it doesn't have to be extremely tight in order to be accurate, which is very nice. And pretty much the most common size pulley that you'll see is a 20 tooth. So if we go 20 tooth times 2 millimeters per tooth, we know that that motor turning one revolution moves this belt, as well as anything attached to this belt, by 40 millimeters. And so on one end of this belt, we've got our motor with a pulley attached to it, and the belt wrapped around that pulley. On the other end of this belt, we've got another pulley that's not attached to a motor at all. It's just around bearings. We call this an idler pulley. It's just, and we can also call it a tensioner. Potentially, we can use it tight. We can pull this forward or back in order to tighten or loosen the belt, and then just tighten it in place. Or we can use a screw, or we can use hydraulics to do that. We can have a separate wheel that does the tensioning, and this wheel just stays still. But whatever the case, we need at least two pulleys. And then in the middle, we can attach something to the belt, and it goes back and forth. Advantage, it's cheap and goes pretty fast, or can go pretty fast. Yeah, that's mainly. They are also very accurate. You can only get so accurate as far as the steps, because you're moving 40 millimeters for a turn, which is what gives you your speed, which is probably what you want more than anything if you're using a belt. So you lose a little bit of the bottom end precision, but it's still very tight. So it's like 1/80th of a turn, or 80 steps to go a millimeter, which means you get precision of 1/80th of a millimeter, which, I mean, you can measure that with calipers, but it might be within the margin of error depending on the calipers you're using. So obviously you can also get bigger belts. They make wider versions of GT2 belts, and they just make different belt standards entirely. Laser cutters, you see a lot of HD belts, HDT, like 3M and 5M, which are 3mm and 5mm pitch respectively. And the advantage there is just they're tougher, they're thicker, they don't vibrate as much. You can put more torque through them. Disadvantage is they're bigger, they cost more, they're heavier, and they need to be they need a lot more tension to stay precise compared to a GT2 belt. And then there are a million other kinds of belts. Those are just probably the two most common that you see. But what if you don't want a belt? There's another option you can do is just use like a screw. So you could take just like a threaded rod, with the thread from a machine screw. Take a nut from that also had the threaded from a machine screw. Put it on the threaded rod. Rotate the rod, but you don't let the nut rotate, and the nut moves it up and down the rod. Problem here is that it's not really meant for that. It's going to wear out. It's going to make a lot of friction. It's not going to be accurate. If it's something that you're going to do, I mean, rarely as like an adjustment, yeah, you can get away with it. If it's something that you're going to do like over and over again 1,000 times in a minute, 1,000 times an hour, whatever the case, or even say 100 times a day, this is going to be wearing out pretty fast. So they make different kinds of screws. They're specifically designed for this use case. Now they make these things called trapezoidal screws. So instead of the thread kind of being roughly shaped like a triangle, like on a regular screw, it's more of a trapezoidal pattern. And now technically Acme screws are a subset of these. So if you're familiar with Acme screws, those are just trapezoidal screws, a type of trapezoidal screws. Metric trapezoidal screws are technically not Acme, although sometimes they get called that anyway. That's a weird noise. So you get these like brass nuts that have screw holes in them, so you can screw them apart. And then you run the threaded rod through your part, through the brass. It's a nut, but flange, I think, would be correct, more accurate term. It's more of a brass flange, but they call it a brass nut. So you run in your rod through there, moves back and forth. Not necessarily very accurate. Depends on who you get it, or who makes them. Some of them are pretty precise, but they're never going to be super accurate because that's not what this is meant for. What they can do is they can get you close enough for a lot of things that it doesn't matter. Or if you design them so that they're working against a force. So maybe you've got like maybe you're just using them to lift something up. So the force of gravity is always pushing down. Well, then the backlash doesn't matter so much. If you're moving things back and forth, you can potentially get away with using some springs and things like that. The added complexity makes it really not worth the effort. simpler approach is just use two of these nuts, these flanges, and one of them is just designed to tighten down with no adjustments. The other one has like 3 millimeters, 2 millimeters, even just like 1 millimeter of adjustment to it. That way you can tighten it against the actual pitch of the rod, and you can get pretty high accuracy out of it at that point, at least high enough that you can use like backlash compensation in the firmware to deal with whatever issues might remain. One huge advantage here, and also disadvantage, is that these can turn very slow. So you can get these threaded rods like an M8 one that rotates and only moves that nut, and the part attached to that nut, by 2 millimeters every time that motor turns. Remember, we can stop that motor 3,200 times in a turn. So now we can stop that motor 1,600 times in a millimeter, which is great if you need the precision. Awesome if you need the precision. Not so great if you want to go really fast, because the top speed of the motor is basically the same. Maybe a little higher RPM just because there's less load on it. It's going to be very close to the same, which means, going from 40 millimeters to 2 millimeters, now you're 20 times slower. So that's not great. Now you can get rods that are threaded rods that are 4 millimeter pitch or 8 millimeter pitch. Actually, they're still 2 millimeter pitch, but they're so they have multiple starts instead of just one screw thread. They've two pitches. Will have two threads starting on opposite sides on either side of the screw, or you can get even a 4-pitch, or a 4 thread, that is. So a 4 thread would be like 8 millimeters per turn, which is 4 times faster. Still a lot more torque. So you got to balance it out. Maybe all you need is very slow movement and lots of torque. Then you've got maybe you want it to go relatively fast, and you're just using screws for I don't know what reason. Well, then you can use an 8. It depends on what you need. So then there's one more class that's commonly used, and it's still a screw and it still has a nut, but the nut is a ball bearing, or it's a housing for ball bearings that circulate through and run against the face of the screw. So the threads of the screw, instead of being like sharp cuts, they're rounded to match the balls that are going to run in them. Can give you quite a bit of force, potentially less force than like a trapezoidal screw, because the trapezoidal screw can have a very tight pitch, and generally these ball bearings have less tight pitches. So you might get a 1 to 8 as like a standard. So like 8 millimeters movement for one turn. That's kind of like a more standard thing than the 2 millimeters per one turn that you see with trapezoidal threads. So a little bit less torque, although in theory the threads themselves can handle more torque. So if you've got a bigger motor, something that would be too much for a trapezoidal thread, it would work with this, at least in theory. Also, at least some of them allow you to change out the balls in the housing, the ball bearings, which means that you can, at least potentially on those models, you can buy the cheap stuff and then just change out your ball bearings for high quality ball bearings, and there's a pretty good chance that it's going to work well for you, at least for a while. If it's not hardened, then you're going to have a bad time eventually. But even the cheap stuff, without changing the balls out or doing anything like that, usually pretty good quality. And part of that is that even the cheap stuff's not that cheap. Right? It might be 10 times more than a trapezoidal, probably more than that. for similar quality across the board. So yeah, they're crazy expensive. But in theory, they can give you the best of all worlds except for torque multiplication. But if you can afford to run these, you can afford to run better motors and bigger drivers, so it doesn't matter anyway. Okay, so that I believe covers all the basics of linear motion robotics. And I'm almost back to the main road, although I am way outside of the historic district. So thanks for watching, and see you next time. Goodbye, Internet.